This diagram is supposed to represent a sphere traveling on a circular path of radius r. This equation here relates the arc length to the radius of the circle and the sphere's angular displacement, the magnitude of the angular displacement. Arc length is equal to the radius times the magnitude of the angular displacement. The angular displacement must be measured in radians. The arc length and the radius are measured in meters. If we divide both sides of this equation by delta t, we get this very useful expression, which states that the tangential speed of the sphere is equal to the radius of the circle times the angular speed of the sphere. And the unit of angular speed is the radian per second. The unit of tangential speed is the meter per second. Now suppose that this is picking up tangential speed. Then we could use this expression, the definition of acceleration. The tangential acceleration is equal to the change in the tangential speed divided by the time interval over which that change occurs. But isn't the change in the tangential speed simply equal to the change in r omega, but the radius is constant since it's a circle? So we end up with the radius of the circle times the change in the angular speed over the time interval over which that change in angular speed occurs. This quantity here, delta omega, the change in angular speed over the change in time, is called the angular acceleration, alpha, and its unit is the radian per second squared. So if we multiply the angular acceleration magnitude by the radius of the circle, we get the tangential acceleration magnitude. Suppose we have a sphere which is accelerating tangentially along a circular path. We learned previously that the tangential acceleration is equal to the change in the tangential speed divided by the time interval, where the tangential speed, we learn, is equal to r times the magnitude of the angular speed. Since the radius is a constant, we can write this as r delta omega over delta t, where the tangential acceleration then is equal to r times the angular acceleration, symbol alpha. But because this sphere is traveling in a circle, doesn't it also have a centripetal acceleration or radial acceleration, AR? And we learned previously that radial acceleration is equal to the tangential speed squared divided by the radius of the circle. This equation was derived by Christian Huygens. So this sphere here actually has two accelerations going on simultaneously. If we use the Pythagorean theorem, we see that the acceleration of this sphere then is equal to the square root of the tangential acceleration squared plus the radial acceleration squared. The direction of the acceleration we could find using a trigonometric function. So this would have to be the direction of the net force as well. Remember that the acceleration is always in the direction of the net force. A wheel rolls along a surface without slipping. The distance its center of mass, which is at the axle, travels, x, should be equal to the arc length, s, that was in contact with the surface as it rolled. You know, if you would put paint on this wheel and then roll it across the surface, the paint would leave a track. And the length of that track would be equal to the amount of arc length here that lost the paint if the wheel doesn't slip. If we take x, the distance that the axle traveled, and divide it by the time, that should be equal to the arc length divided by the time, where the arc length divided by the time is equal to the tangential speed of the wheel. And x over delta t would be equal to the speed of the center of mass of the wheel, okay, which is directed to the right. But didn't we learn previously that the tangential speed was equal to the radius of the wheel times its angular speed? So the center of mass speed of a wheel as it rolls without slipping is equal to the radius of the wheel times the angular speed. Now that's interesting because the tangential speed of the wheel, if it were just in pure rotation, would be equal to r omega. We learned that previously. If it's rolling without slipping, its center of mass travels at this speed as well, r omega. So we can conclude from this that if a wheel is rolling without slipping, the top of the wheel is traveling twice as fast as the axle, and the point of contact, that is here, must always be instantaneously at rest. A wheel rolling along a surface without slipping can be thought of as follows: a wheel in pure rotation, and at the same time a wheel in pure translation. Now, a wheel in pure rotation has its perimeter traveling at r omega. A wheel in pure translation has every part of it traveling at r omega. If we add these two together, we get a wheel rolling without slipping. So when you add this r omega to this r omega, you get 2r omega. At the axle, you would get r omega, and at the point of contact P, you would get 0. So the speed at the top is equal to 2r omega. The speed at the center of mass is equal to r omega, and the speed at the point of contact is equal to 0. This helps explain, by the way, why you get mud splashed up on your back when you ride a bicycle through a puddle of water. Because when the mud leaves the top of the wheel, you notice that it's traveling at approximately twice your speed. Because remember, your speed would be the same as the axle, r omega, because the seat is essentially connected to the axle. But the mud that leaves the wheel at the top is traveling about twice your speed, so it catches up to you and you get mud on your back. So that's why it's a good idea to have fenders on the bicycle. If a wheel is rolling without slipping, we saw that the velocity of the center of mass was equal to the radius of the wheel times the angular velocity. Suppose that somehow the wheel is accelerating and at the same time not slipping. Then we can take a look at the change in the velocity of the center of mass with respect to time and set that equal to the radius, which is constant, times the change in the angular velocity with respect to time. So we have delta VCOM over delta T is equal to R times delta omega over delta T. So the change in the velocity of the center of mass with respect to time then, or the acceleration of the center of mass, is equal to the radius of the wheel times alpha. This is only true when there's no slipping. A little bit later on, we'll be talking about Newton's second law of rotation. And there we'll see that it's a net torque that causes an angular acceleration. Torque can be thought of as a twisting force. It is defined as the magnitude of the force multiplied by the lever arm, and it has the units, the Newton meter. If we wanted to find the torque about an axis that runs perpendicular to the board at this green sphere, we would take the weight, which acts at the center of mass of the meter stick, and multiply it by the lever arm, which is the perpendicular distance from the line of action of the force and the axis of rotation. So the lever arm, L, would be this distance here, which in this case would be a half meter. So the torque then about this axis here is equal to the weight times L. Okay, if the torque causes a clockwise rotation, as the weight of the meter stick does, we say that it's a negative torque. If the torque causes a counterclockwise rotation, then we say it's positive. The torque that the weight of my arm causes about my shoulder would be 0 in this case, because the line of action of the weight runs right through my shoulder. And you notice that it's not too difficult to hold your arm up in the air like this. But when I hold my arm out like this, now the weight of my arm acts straight downward, and we have a lever arm, so there is a definite torque, and I can sense that. And it's definitely harder to hold my arm like this. Suppose we wanted to figure out the torque about this axis of rotation, and in addition to the weight of the meter stick, we also have a force that's acting into the first quadrant like this. To find the torque, we would have to take the weight of the meter stick multiplied by the lever arm, L, and note that this causes a clockwise torque, so it's negative. And then we would need to add it to the torque caused by this force here. So we take this force, the magnitude of that force, F, and then multiply that by its lever arm. Okay, this represents the line of action of the force, and the lever arm would be equal to perpendicular distance. L. We call it L2. So we would take this force, multiply it by L2. Note that it causes a counterclockwise torque, so it's positive. And adding these two torques together, you get the net torque. This toy elephant, mounted on the meter stick, balanced on my hand, is in a state of equilibrium. Okay, what does that mean? It means that if you add up all the forces on the meter stick and elephant, you should get 0. In addition, the sum of the torques about any axis of rotation should also equal 0. So for the sum of the forces equals 0, shouldn't the weight of the elephant plus the weight of the meter stick equal the normal force, which is exerted on the meter stick at my hands? And shouldn't the torque exerted by the elephant be equal to the torque exerted by the meter stick's weight if we sum those torques about my hand? Okay, so the weight of the elephant multiplied by the lever arm from here to here should be equal to the weight of the meter stick multiplied by the lever arm measured from here to here. This broom is in a state of equilibrium, which means that the sum of the forces on the broom equals 0, and the sum of the torques about any axis is equal to 0. So the weight of the broom should be equal to the normal force, which is exerted on the broom by my hand. And the sum of the torques about any axis, okay, let's choose my hand as the axis, should equal to 0. So that means that the torque that this side of the broom exerts should be equal to the torque that this side of the broom exerts about this axis. And of course, the torques are oppositely directed. One is positive and one is negative. When you add them up, you should get 0 for equilibrium. So which end weighs more? Does this end weigh more, or does this end weigh more? Well, wouldn't this end have to weigh more? Because you'll notice that its center of mass, which would be about right here, is pretty close to the fulcrum. Whereas the center of mass of this end of the broom, which would be about right here, is pretty far away from the fulcrum. So wouldn't this have to weigh less than this end here? Now we can check this by cutting this in half. Okay, actually cutting right here. So separating this end of the broom from the handle and then weighing each part. So this end of the broom has a mass of 224 grams. If you want to figure out its weight, you would have to first convert that into kilograms. So that would be 0.224 kilograms. And if you wanted to figure out its weight, you would multiply that by 10 meters per second squared. So we would have about 2.24 newtons. Now let's take a look at this end of the broom. And you can clearly see that this end of the broom weighs a lot more. The moment of inertia of a body about an axis can be thought of as a characterization of its rotational sluggishness about that axis. To find the moment of inertia, you use the following equation. Sigma summation of all the masses that make up the body multiplied by the distance that those masses are perpendicularly to the axis of rotation, and you must square that distance. So we have I is equal to sigma mi Ri squared from I is equal to 1 to n. Take a look at this body here. It has a certain mass, and its moment of inertia could be calculated by summing up all the pieces of mass multiplied by their distance squared to the axis of rotation. Its moment of inertia characterizes its rotational sluggishness. So quantifies the difficulty in rotating it like this. If I do this, it has the same mass, but you see now that the R's are much different. This should have a larger moment of inertia. And indeed, it is harder to rotate. And now watch this. When I allow it to collapse, you notice it starts to spin faster. Okay, and we'll address that in a future topic. Newton's second law for translation is net force is equal to mass times acceleration. Newton's second law for rotation is not derivable, but can be understood by analogy. Instead of net force, we have net torque. Instead of acceleration, we have angular acceleration. And instead of mass, we have a physical quantity which characterizes the rotational sluggishness of the body upon which the net torque acts. We call this moment of inertia, and its symbol that we use is I. The unit of moment of inertia can be found by solving for I, and you get the Newton meter, the unit of torque, divided by the unit of angular acceleration, which is the per second squared. So what you get for the unit of moment of inertia is the kilogram meter squared. If an object is just rotating due to a torque, then you only need to use Newton's second law of rotation. If an object is only translating due to a net force, then you only need to use Newton's second law of translation. Let's talk about the energy of a body rolling down a hill, like this disc, or this hoop. When each of these bodies started, they were at the top of a hill, and their energy was in the form of potential energy, mgh, where m is the mass of the body, h is the height of the body, and g, of course, is the acceleration due to gravity. At the bottom of the hill, the body has kinetic energy. But we can think of the body as having two types of motion. It has translational motion, right, because it's rolling. So we can speak about its translational kinetic energy. But since it's rotating, it also has rotational kinetic energy. Now the translational kinetic energy is 1/2 times the mass of the body times its speed at the bottom of the hill squared, and that's the speed of its center of mass. How about its rotational? Okay, let's look at it as being in pure rotation. So we can think of this disk as consisting of a huge number of individual masses. But let's just represent 4 and call this M1 at a distance R1 and traveling at a speed V1. Let's call this M2 at a distance R2 traveling at a speed V2. And this one we'll call M3 at a distance R3 traveling at a speed V3. And this one is M4 at a distance R4 traveling at a speed V4. And of course there's thousands of others that we could draw that make up this disk. So let's take a look at the kinetic energy of this piece, of this piece, of this piece, and of this piece as they travel in a circle, and all the others that make up this disk, and add them up. And then we have an expression for the kinetic energy of the disk in rotation. So I would take 1/2 times the mass of each piece, mi, we'll call the mass of each piece, times the speed of each piece, and I'll call that vi, square it, and then I'll add all those up, all those kinetic energies up from 1 to however many number there are, probably thousands. So that's the kinetic energy due to rotation. And if we add these two kinetic energies together, okay, from conservation of mechanical energy, we should get the original potential energy. Now let's take a look at this expression. This is pretty hard to use in that form. 1/2 is a constant, so I'm going to bring it out in front of the summation sign. So that leaves me with mi vi squared from I is equal to 1 to n. But isn't the speed of each one of these pieces equal to r times omega? So we can rewrite the speed as Ri omega. And I'm not going to put an I by the omega because the angular speed for each one of these is the same as the other. So omega is a constant. So I'm going to take this expression and substitute it into this equation here. And I'll do that over here. And I get 1/2 sigma I is equal to 1 to n mi Ri squared omega squared. But we should recognize this quantity as being equal to the moment of inertia of the body about its central axis. So I can replace this with I. So I have 1/2 I omega squared then is equal to the rotational kinetic energy. So we can state then that the potential energy at the top of the hill is equal to the translational kinetic energy, 1/2 m VCOM squared, plus the rotational kinetic energy, 1/2 I about the center of mass, omega squared. So we can use this equation then, for example, to predict the speed of the center of mass, knowing the acceleration due to gravity, the height, and some other things. Okay, let's take a look at that. Okay, what I'm going to do here is first treat this as a disk. Actually, why don't we just not specify what the object is? Right? It could be a solid sphere, it could be a hoop, or a disk, or something else that's rolling down the hill. So I'll just leave it as ICOM. And I want to solve this for VCOM to see what the speed is at the bottom of the hill. So if we do that, we get first 1/2 m VCOM squared is equal to mgh minus 1/2 I COM omega squared. Now, omega, can't we express, if this body is rolling without slipping, can't we express that in terms of VCOM and R, right? The radius of the body that's rolling down the hill. We call that VCOM is equal to R omega. So I'm going to substitute this into there. Okay, now I'm going to get the VCOMs together, and I'll continue that right here. So there's our expression for the speed of the center of mass of a rolling body. Now what's interesting about this is when we do substitute in the moment of inertia for the rolling body, you notice that mass will appear in each term under the radical, so that gets kicked out of town. But you'll also have an r squared here in the numerator for the ICOM, but you have an r squared here in the denominator, so even r squared gets kicked out of town. So what that shows us is that, for example, two disks, regardless of their mass and radius, will tie and race down a hill. Two hoops, regardless of their mass and radius, will tie each other in a race down a hill. Two solid spheres, ditto. This equation also helps us predict who will win a race, a disk or a hoop rolling down a hill. So to predict that, you would want to substitute in the moment of inertia for a disk, solve for VCOM, and then substitute in the moment of inertia for a hoop, solve for VCOM, and you'll see which one has a higher speed at any given moment as it races down a hill. Let's try this. Okay, let's first look at the disk. I for a disk is equal to 1/2 mr squared. Divide that by r squared. Simplifying, we get now let's try the hoop. The speed of the center mass of the hoop is equal to the square root of 2 mgh divided by m plus I for a hoop is just mr squared. We divide that by r squared. So we get the square root of, so I think you can see by comparing the speed of the hoop and the speed of the disk that the hoop has a lower speed than the disk. So the disk should win the race. What is the direction of angular momentum? Well, angular momentum is equal to the moment of inertia times the angular velocity. So whatever the direction of the angular velocity is also the direction of the angular momentum. The way you figure out the direction of the angular momentum is by simply curling your fingers in the direction that the object is rotating. Okay, so suppose I rotate this like this, and you notice that it's moving from your point of view, okay, this is moving in a counterclockwise manner. If I curl my fingers in the direction of rotation, my thumb points in the direction of the angular momentum, of course also the angular velocity. So the direction of this wheel's angular momentum is that way. Now, suppose I stop spinning it and I simply support it by this string. Now the force of gravity is going to exert a torque on it and cause it to rotate like that. What's the direction of that angular momentum? Well, using the right hand rule, I curl my fingers in the direction of rotation and my thumb points that way, away from you, the viewer. Now let's combine these two rotations, these two angular momenta. Remember, angular momentum is a vector quantity. So now we have an angular momentum this way, and if I support it by this string, we get an angular momentum that way. If we combine those two angular momenta, since they're vectors and we can add them head to tail, don't we get a net angular momentum in this direction? Let's try it. This motion, by the way, is referred to as precession. Our Earth precesses. It takes about 26,000 years for the Earth to go around once. Angular momentum, L, is equal to the moment of inertia, I, times the angular velocity, omega. This sphere here has a moment of inertia, I, but it has no angular velocity at the moment. If I want to give it an angular velocity, I have to exert a torque on it. Something like that. So now it has an angular velocity. If I multiply the angular velocity times I, the moment of inertia, I would get the quantity which we call angular momentum. The unit of angular momentum is the unit of moment of inertia, which is the kilogram meters squared, multiplied by the unit of angular velocity, which is the per second. Now let's take a look at the relationship between net torque and angular momentum. Recall that I had to exert a net torque on the sphere in order to change its angular velocity and its angular momentum. So let's go back to the first equation I displayed. L is equal to I omega. And let's write it as a change in L per change in time. On the other side of the equal sign then, we would want to write I times change in omega divided by the change in time, because we're keeping the moment of inertia of the sphere the same. Now we recognize the change in omega divided by the change in time as alpha. So we can rewrite this equation as delta L over delta T is equal to I times alpha. Do you recall what I times alpha is equal to? That's right, the net torque. So the net torque is I alpha. So replacing I alpha with net torque, we have that the net torque then is equal to the change in the angular momentum, delta L, divided by the change in time. Do you see that if you do not have the net torque, that is, if the net torque is equal to 0, then the change in the angular momentum divided by the change in time is 0. And this leads to that the change in the angular momentum is equal to 0. Which means that the angular momentum is a constant if there is no net torque. This is known as the conservation of angular momentum. Conservation of angular momentum. If the net torque on a system is 0, then the angular momentum is a constant. Okay, what I'm going to do here is I'm going to give this sphere a spin by exerting a net torque on it. We could figure out its angular momentum by taking I, its moment of inertia, multiplied by its angular velocity. Then what I'm going to do is I'm going to pull on this lower string. And when I pull on this lower string, it causes the sphere to collapse, thus changing its moment of inertia. It will actually reduce its moment of inertia. Because of conservation of angular momentum, and because this force I exert by pulling down on this string doesn't exert any net torque on the system, you would expect the angular velocity to increase. Okay, let's try it. Reminds me of an ice skater. Conservation of angular momentum. If the net torque on a system is equal to 0, then the angular momentum remains a constant. Okay, what I'm going to do here is I'm going to spin this record that is suspended by a string. Its angular momentum would be equal to I, the moment of inertia, which would be 1/2 mr squared because it's a disk, multiplied by its angular velocity. What I'm going to do next is I'm going to drop another record, an identical record, onto the lower record. And when this hits the lower record, there's not going to be any net torque. So the angular momentum should remain the same. But because we have a higher moment of inertia, double what we had before, won't the angular velocity be half? Okay, so let's try this.